So, please return your graded homeworks in order for me to see how we will curve things.
How much is each assignment out of? What,
Each assignment,
yeah, how much do we make it out of? Like out of 10? Or?
each problem is out of 10.
Each problem is out of 10.
Okay. Okay. So, if we have two vector fields, like x is maybe y negative x and 0, y is 0 z and negative y. These are three-dimensional vector fields, so we can view them as vector fields on R3, on the three-dimensional space, okay? And let's have some colors here. So this is the blue one. So actually this is your three-dimensional space. X, Y, and Z. This vector field, anybody doesn't understand this? Anybody doesn't understand this symbol? I think it's, you guys have to ask, right?
No, sorry, last course, last lecture you had of a manifold.
Yes.
Now you're
So R3, what do you think of R3? Anybody thinks R3 is a manifold or not? Who agrees that R3 is a manifold? This three-dimensional space that we live in is a manifold. Who doesn't agree that it's a manifold? Anybody remember what do you mean by a manifold? A manifold that is
everywhere locally.
that locally looks like a flat space. Actually, R3 is in fact a flat space. It is the flat space. Okay? So it is the simplest manifold ever, and the map that will map every point, every neighborhood point to a flat space. The map is simply identity, right? So R3 is a manifold, then we can define, like any manifold, we can define velocity fields, velocity vectors in a manifold. So these two velocity vectors, they are vector fields on that manifold. So for example, this blue vector is simply at this point. What do we mean by a vector field? At each point, it gives you what?
What?
Gives you what?
A tangent
Velocity
vector.
vector, right? So here at this point gives you this vector, at this point gives you that vector, this vector, and so, okay? And it's everywhere. So here it's, down here is something like this, over there is something like that, right? It's at any point in the R3 domain, it gives you a vector. This red guy, at any point, gives you another vector. So maybe at this point gives you that vector, here it gives you that vector, and so, okay? So the question is, so I'm given two vector fields, meaning I'm given two velocity vectors everywhere. These are two and maybe independent velocity vectors, but I have 3 degrees of freedom in my manifold, x, y, and z, right? So using these two velocity fields only, velocity vectors only, can I cover every point? Can I go to every point, starting from any point?
No.
Well, if I start from here, and if I have the ability to move in independent 3 velocities, right? For sure I will move in all the directions, right? So starting at any point, and if these were 3 vectors, and you have 3 degrees of freedom, and these 3 velocity vectors were independent, then of course I can go anywhere, right? But for example, if I start here, I have no options but either follow this red guy or follow that blue guy, right? So just at any point, I'm moving in a plane, okay? The question is, can I go everywhere or I am confined to some surface? This is one of the questions. In other words, from a geometrical point of view, does there exist a surface in R3, okay, some surface, such that this X and Y are always tangent to that surface? If such a surface exists, then if I start from here, I will just move along that surface and I will never leave it, because these velocities are always tangent to that surface, okay, which is embedded in the larger space. Okay, so let's try to do it mathematically. I mean, this is pure geometry, right? It's just pure geometry. You have two vectors that at each point gives you two velocity vectors, and you're asking, these two vectors live in a bigger space in R3, and I'm asking, do they live in a smaller space? That's it. That in itself lives in R3, okay? Any question about the geometrical meaning, the geometrical interpretation of that question? Do you understand this question or not? I mean, I don't care how we're going to do it. I mean, this we'll discuss. But do you understand the question or not? Anybody does understand the question? Feel free to ask, please. Any question about the question? Yes, you?
I'm just wondering, so this surface will be very, okay.
Maybe, I don't know. I don't know the shape of the surface, but I'm asking, does there exist a surface? Because this has serious repercussions, serious consequences. What is the consequence? Whatever the surface looks like, here is the surface. If I start at this point, then I will never leave that surface. Okay? And this surface is just a slice in R3. So if you're asking, is I start here following these vectors only, if I start here following these vectors only, maybe I follow the blue one until this point, and then I decide to follow the black one, the red one, and so on, keep switching. Just by following these two vectors only, can you go anywhere in R3? If you start from some point. This is the point. I mean, we don't know the answer yet. We don't know the answer. This question is equivalent to this question, which is, okay, if these two vectors are tangent to some surface at every point, this means that if you follow them, you will never leave that surface. So I'm asking now, does there exist a surface in R3 such that these two vectors are always tangent to it? Okay, this is the geometrical question. Let's answer that. Let's try first to interpret this mathematically. A surface in R3, sphere or a circle or whatever, paraboloid or whatever, how do you represent it? If I give you a problem, here is a surface. Or you're describing the surface to me. What are you giving me? What are you giving me? How do you represent the surface in R3? The equation of the surface, right? There is some equation, maybe if it's a sphere, it's x squared plus y squared plus z squared. Some function is equal to a constant on the surface, right? So some function is equal to a constant. This is how we write, how we express, how we describe surfaces mathematically, right? Some equation. Okay, so I'm going to interpret this. Does there exist a surface in R3, meaning a function that takes any point and gives you a real number, right? This function is the one that represents the surface. It's a sphere, it's x squared plus y squared plus z squared. It's a circle, in the xy plane, it's x squared plus y squared. It's a parabola, in the xy plane, it's y equals x squared, right? Or y minus x squared equals z. Any question about that? So does there exist a function representing the surface such that what? If these guys are tangent to the surface represented by this function, how they are related mathematically to the function? If this is the surface, and I'm asking if this vector is tangent, x, is it tangent to this surface that is represented by the function or constant? How can we write that back. How do you check it mathematically? If I give you a function, here is a function, x squared y squared equals z squared. And I give you vector, and I'm asking you, is this vector tangent to the function? How do you check it?
Directional derivative.
Say it again?
Directional derivative. Take the gradient of the surface.
Yeah, that we were heading there, but no, I need it just slowly. How do you check it?
Which-
Geometrically first, how do you check it?
If it's normal to that.
Well, if you're given a function, what can you get out of this function? What vector can you get out of this function? The derivative, yeah, we call it what?
Tangent.
The gradient. The gradient is a vector points in one direction.
Normal.
So this is the gradient. If I have f, I simply can get this vector. Then now I should check what? That my x is perpendicular to the gradient, which means what?
It's
X dotted with nabla f is equal to
0.
0. This is my check, right? And I'm asking now for two vectors. It's x dotted f and y dotted nabla f, right? These should happen simultaneously. I should check that. Any question about this? Is the condition that we need to check. Any question? Okay, in our differential geometric language, this has a name. What's its name? This guy? Yeah, just day before yesterday, we discussed it in detail. What's the name of this guy? Yes, it's the directional derivative, or in the differential geometric language, it's the lead derivative of f along x, the lead derivative of y along f. That's fine. This is just a language. I mean, I don't care much if you want to compute it from here or there, because they are actually exactly the same expression. If you are more comfortable with this, write it as y dotted with number f or x dotted with number f. Okay. So let's check that. I have my vector x and my function f, and I want to get Lxf. What's that? This is the first component of x, which is y. Please bear with me here to see how I'm doing it. First component of x times partial f partial the first coordinates. Second component of x times partial f partial the second coordinate. Third component of x is 0. This guy should be 0, right? I don't know if such an f exists or not yet. I'm asking, does such an f exist? Okay, so I need to solve this equation to see if it exists or not simultaneously with Lyf, again, similarly. First component of y is 0, second component of y is z, partial f, partial the second coordinate. Third component of y is negative y, partial f, partial the third coordinate. This should be 0. These two equations should be satisfied simultaneously in order for the two vectors to be tangent everywhere to the surface represented by the function. Any questions so far? Any questions? Yes, Mikhail.
What you have written before the I dot, so it's an off?
What is that?
Yeah, in the,
This one?
yeah, it was.
And.
And.
Place it with a comma, that's fine. These two conditions simultaneously, they have to be satisfied. Okay? What type of equation is this? What type of equation? What type of equation is that? It's what?
Differential equation? Partial differential?
Yeah, it's partial differential equation, right? It's partial differential equation. So this question that we posed is that starting with two vectors, will they always remain tangent to some surface embedded in the higher dimensional space or not? It always reduced to or boiled down to solving partial differential equations, which is hard, right? So if you want to really know the answer to this question, you should try to solve the partial differential equation. And if you solve it, you find the function, that's a great yes, so the answer will be yes. If you couldn't solve it, I don't know, maybe you just not good enough at PDEs to solve this thing, right? So we need something simpler some simple check to answer this question. But before doing that, I'll do it here because this PDE turns out to be easy. In order to solve this, can you find a function that satisfies this particular equation? Yes, indeed. Any function of this form, x squared plus y squared plus some constant, and the constant may be a function of z. Why? Because if you differentiate with respect to x, you get 2x. Differentiate with respect to y, you get 2y, and then the 2xy's will cancel each other. Okay? And from here, it's the exact same thing. F will be what? Y squared plus z squared plus any function of x, right? And if you want to satisfy them simultaneously, then obviously your function will be x squared plus y squared plus z squared plus some constant, right? So the answer to this question is indeed yes. There exists a surface that is embedded in R3 such that these two vectors will always be tangent to that surface. And what does this surface look like? It's a sphere. Okay? It's a sphere. Which means that if you start at any point, you will never leave that sphere. If you start at any point and you are only allowed to flow along these guys, you will never leave that sphere. The sphere is just a slice in R3. Okay, so you certainly cannot reach all the points in R3, and you live on a smaller dimensional manifold, or what we call sub-manifold. Okay? Any question about this? Like I said, this is tedious check. I will not be able to solve PDEs all the time, and I don't require you to know how to solve PDEs. This is not how we're going to do it. We'll do it much easier thanks to a theorem by Frobenius, and we will define it now. How to use this theorem, just a piece of cake. But we need to understand the underpinning geometrical concept. This is the underpinning concept. I'm having 2 or 3 velocity vectors or whatever, and I want to see, do they cover all the space or not? Or they cover just only subspace, submanifold. In order to give you the theorem, I need some additional language. So this is, I guess, our 8th word. It's distribution. Any question before going to this theorem? Any question? Any question about that, or these two words? Okay. A distribution, we give it the name delta. On a manifold M, gives you